We are picking up this video where we left off last time with reactions. We concluded our discussion of single replacement and will now discuss double replacement as well as some others. Double replacement is defined as a reaction where two ionic compounds switch partners to make two new ionic compounds. So as you can see in the example, Na was paired with OH, but on the product side, Na is now paired with Cl. And Fe was paired with Cl initially, and now our Fe is with the OH. The same thing is true for the second example. It was KCl, now it's K with SO4, and then copper switched as well. When we predict the products for these, again, just like everything else, we assume things are ionic. I sometimes find it helpful to use a visual. So the Ca is with Cl, and Na is with OH. The Ca is going to end up combining with our OH, and our Na is going to end up combining with our Cl. So we have to cross our charges. So calcium is +2, OH is -1. When they're crossed, you get CaOH2. And then Na is +1, and Cl is -1. So when combined, you get NaCl. Please pause the video to try the second example. I'll help you out with some charges. NH4 should be +1, and sulfate is -2. Your answer should be NH4F and VaSO4. It does not make a difference which one is written first. So if you wrote VaSO4 plus NH4F, it's the exact same thing. Now let's kind of break our double replacement reactions up into some subcategories. The first double replacement subcategory is precipitation. Precipitation is characterized by a solid product that is being created, known as a precipitate, hence the name. These are based on the solubility rules, which we'll cover in a later chapter. So NaCl plus AgNO3 means AgCl solid plus NaNO3. You would identify this as precipitation because you see that there's a solid product, and you have 4 ionic compounds to begin with. We're going to briefly talk about net ionic equations. A net ionic equation is when we take that solid and we break it into its ions. So the solid in this example is AgCl. And if I'm going to break it apart, I know it's going to be Ag plus Cl. And then I use my periodic table to see that it's Ag +1 and Cl -1. The second subgroup of double replacement reactions is neutralization. And these are characterized by an acid, which starts with an H, plus a base, which ends in an OH, producing a salt, any ionic compound, plus water. And then I provided you an example below. Okay, you'll notice the H, you'll notice the OH, we have salt, and we have water. Let's cover our next reaction type. The fifth reaction type is combustion. A combustion reaction is defined as a hydrocarbon, so something with H's and C's, right? Hydrocarbon, plus oxygen to produce the products carbon dioxide and water. When you see products carbon dioxide and water, automatically combustion. And I provided you with an example. Predicting products for these is probably the easiest of them all. You see that we have a hydrocarbon plus oxygen, and automatically you should think combustion. So the products produced are CO2 plus water. The same thing is true for the second one. And then you would, of course, use your balancing equation knowledge to balance it out appropriately. What I would like you to do is try these practice problems. The first thing you want to do is identify the reaction type based on what it says. Okay? And then from that, predict the products. So we'll do the first one. Sodium plus oxygen. We have 2 elements. The only thing we could possibly do with them is combine them. So this is going to be a combination or synthesis reaction. So now that we know that, we're going to take our Na with its charge of +1 and our oxygen with its charge of -2, cross our charges to produce Na2O. Please pause the video and try the remaining examples. Here are the answers to the practice problems. For NH3, it's one thing, so the only thing you can do is break it apart. So it's going to break into N and H, which are both diatomic. The next one has somebody who's single, the Zn, combined with a compound. So that means it has to be single replacement. And you'll go ahead and you'll do your single replacement. The H2 ends up by itself, and the Zn and the other combined. The next one, again, is one thing, so it has to turn into 2. It's just going to break into Ba and S. They do not get 2s because they are not diatomic. The next one, the C6H12O6, is a hydrocarbon plus oxygen, so the products are CO2 and water. KBr and Cl2, again, we have somebody who's single, therefore it has to be single replacement. This time it's a non-metal, so the non-metal replaces the non-metal. Again, you cross your charges. And finally, the last one is double replacement because you have 2 compounds, and you have to switch your charges around to produce MgSO3 and water. Let's continue our study by covering a different type of reaction. The last reaction type we're going to talk about is oxidation-reduction. I would have to tell you, or your instructor would have to tell you, that you were dealing with an oxidation-reduction reaction because they look very similar to the other ones we've previously discussed. They always occur in pairs, and they're based on the movement of electrons. The acronym you want to use is OIL-RIG, which stands for oxidation is loss, and again, loss of electrons. So that's going to be producing something that's more positive than before. And reduction is gain of electrons. So that's going to become more negative than it was before. We have something called an oxidation number or oxidation state. It's really kind of a fancy word for charge. Okay? For simple ions, most of the time it's just their regular charge on the periodic table. So 1A is +1, 2A is +2, oxygen is -2, hydrogen can be +1 or -1, depending upon if it's combined with a nonmetal or with a metal. And then we have something called an elemental state. Elements that are in their elemental state have an oxidation number of 0. So these are elements when they are by themselves, so like sodium, or just oxygen, or platinum, or just hydrogen. Let's go through some practice problems that relate to oxidation reduction. So here's a sample problem that you could see. It could say, determine the oxidation number for each element below. So for the first example, we'll do the first 2 and I'll have you try the third one. All of these are neutral compounds, so the total charge has to be neutral. H is going to have a +1 charge. We know that each H is going to be +1. And O is -2. So really, you're just telling me what their charges would be. In the next example, our H is going to be +1. Our oxygen is still going to be -2. But normally nitrogen is a -3. If I make it a -3, I don't have a neutral compound. So here's what I need to do. I need an overall charge of 0. So H is +1. O is -2 times 3, which gives me -6. So right now my compound has an overall charge of -5. To make it neutral, nitrogen has to counter that -5 and be our +5. Please pause the video and try the last example. K is in group 1, so it's +1. Oxygen, once again, is -2 times 4, because there are 4 of them, to make -8. +1 and -8 make -7, so our Mn must have a +7 as its oxidation number. The second type of problem that you could see is similar to this second question here. It says, what is oxidized, what is reduced, and are there any spectator ions? A spectator ion is something that keeps the same charge, so the charge remains the same. Very similar to, if you're a spectator at a sport, you're really not affecting the overall result of that game. So what you need to do is you'd look at your reaction, you'd assign oxidation numbers to everything first, and then see what became more positive, what became more negative, and what didn't change. So iron in this first example, okay, we have to look at our NO3. NO3 has a -1 charge. I have 3 of them, so iron has to be +3. Zinc is by itself, so it has an oxidation of 0. On the other side, NO3 again is -1. Because of this 2, iron is +2. And again here, NO3 is -1. And because of this 2, zinc must be +2. So you take a look at what's changed. Iron has gone from +3 to +2. So it became more negative, slightly. So it's reduced. And zinc went from 0 to +2. So it became more positive. So it's oxidized. The NO3 didn't change. So because it didn't change, it's our spectator. Please pause the video and try the second example. PB and O should both be 0 on the reactant side because they're by themselves. And then PB becomes +2 and O becomes -2. So PB went from 0 to +2, positive, so it's oxidized. And oxygen went from 0 to -2, so it's being reduced. The final slide for this video just gives you some examples of where we see redox in real life. Batteries, photosynthesis respiration, rusting, electroplating, and when food spoils. This concludes our study on reactions. The next video will introduce you to some important chemical calculations.